Math. You thought you escaped it in high school, but here it is in college back to haunt you again. Lucky for you, however, I finished most of this stuff in high school. So I now get to make videos and teach you guys how to do it. All right, so today it's just going to be a review of the maths workshop that was supposedly taught to us during the workshops. Excuses. Anyways, we are just going to go over imaginary numbers, vectors, and then derivatives and partial derivatives and all that fun stuff. Please keep in mind that if you have a certain problem you would like me to work through or explain, submit it through the forms that is linked on the website, which is linked to the YouTube About section. Also, I'm just going to link the website to the videos too, so no worries. Or even if you saw the videos on the website in the first place. So yeah, any questions, feel free to contact me and send in those questions. I will happily make a video about them. This is just a broad overview for the most part. So let's get into it. Imaginary numbers. Something we wish never existed in the first place. I mean, if it's your imagination, you might as well pick out the good parts, right? Not the gross. I don't want to say gross. They are helpful, but anyways, imaginary numbers. Let's start with the quadratic equation that we all hopefully know and hate. So x equals negative b plus or minus square root of b squared minus 4ac divided by 2a. Now what this quadratic equation has, is this thing called the discriminant. And the discriminant basically tells us what types of zeros or roots we have in maybe, let's say, like a parabola. And yes, pretty much only a parabola. So we have a parabola, and our parabola can be like over here, maybe it'll be up here, maybe it'll be over here. Wherever it is, it has roots, it has zeros, it has places where the equation equals 0, all right? And these roots are discovered by the discriminant. Let's take a look. Discriminant, b squared minus 4ac. So if our discriminant equals 0, then we have two identical, two plus or minus same roots. This means is that we're just going to have a plus or minus 1, plus or minus 2, so on and so forth as our roots. I'm going to have two of them. If it is greater than 0 and positive, there are two real roots. However, if it is less than 0, there are no real roots. They are all imaginary. And maybe in high school, this is where a teacher stopped and went like, oh yeah, they're all imaginary. That's how life is. Maybe you'll learn it one day. I don't know. Well, you're going to learn it today if you didn't already. I don't know. Imaginary. So imaginary numbers are denoted by this thing called I. Let's go ahead and remove this. They are denoted by I. And I is just fancy for square root of -1. All right, that's it. That's all it is, okay? Why is the square root of -1 imaginary? I don't know. I didn't major in math. I didn't even major in anything yet. I haven't even graduated from college, okay? I equal -1. Poggers. Now then, here's some basic things you should probably memorize, okay? I to the power of 1 equals I, square root of -1. I to the power of 2 is equal to -1 squared, -1. I to the power of 3 is -I, okay? That's just going to be negative square root of -1. All right? And I to the power of 4 is equal to 1. All right? Memorize this relationship. And a really easy way that we can find the value of any I to the power of whatever is by dividing this exponent by the number 4. For example, if we have I to the power of, let's say, 20, well, that's going to be equal to 1. How do I know? 20 divided by 4 is 5. Are there remainders? No. There are no remainders. That means that we're at I to the power of 4. It goes unevenly. However, if we had something like to the power of 21, then that would be -1. Why? Well, 21 divided by 4 is 5. We have a remainder is equal to 1. I to the power of 1, square root of -1. All right? So that is how I works. A complex number, on the other hand, is any number that has an I in it. And they take the form of A plus BI. All right? And every complex number has a conjugate. And that just means that this sign right here switches. So A plus BI becomes A minus BI and vice versa. All right? When we add two conjugates together, when we add A plus BI plus A minus BI, we will get a real number. And that's because the two B's here will cancel out. Okay, they are the same thing. When you add the positive of the same thing of negative, right? So +1 minus 1 equals 0. +2 minus 2 equals 0. Okay, they cancel out, equals 0. However, if we were to subtract them, we get an imaginary. All right? This is because the A's will cancel out. We'll get A minus A. And the B's will get B plus BI. All right? These two will add. And it will give us an imaginary value. So multiplying complex numbers is pretty much the same way as you would multiply your typical FOIL method. So A plus BI times C plus DI, A times C plus C times BI plus A times DI plus, well, BD times I squared, which is -1. So this would just be negative BD. FOIL method, same thing. All right, now what about dividing complex numbers? Well, let's say we've got A plus EI, or actually let's use actual values for this one. Let's say we've got 3 plus I divided by 1 plus 2I, all right? Well, how do we divide this? First step is to multiply it by its complex conjugate, or at least the denominator's complex conjugate. We're going to get 1 minus 2I over 1 minus 2I. And multiplying this, get the following. 3 minus 6I plus I minus 2I squared, divided by 1 minus 2I plus 2I minus 4I squared. And simplifying that, we get 3 minus 5I minus 2 times -1 from that I squared up here, divided by 1 minus 4 times -1. And this is going to give us 5 minus 5I divided by 5. And now we can go ahead and divide this. Dividing this, we get, well, we can separate the denominator and get 5 over 5 minus 5I over 5, and we end up with 1 minus I. So to recap, what we do is we multiply by the complex conjugate of the denominator, and then we just simplify until we get something nice and simple like this, which we can turn into, we can separate the bottom part into two, a real portion and an imaginary, and we can go ahead and solve, right? So another thing that was covered was the modulus and argument, or polar coordinates. I don't know why they call it that, so we're just going to do polar coordinates. So polar coordinates are comprised of an r and a theta coordinate. What happens is that we have this kind of like a 3D grid in some cases. And actually, no, it's easier. Let's just go at this. Let's keep it 2D, keep it simple. Got a 2D grid, and your r is essentially the distance from the origin. Your theta is the angle from the x-axis in a counterclockwise fashion. This is theta. Theta is also called argument, r is also called modulus, but please just call them r and theta. No need to be fancy here. Literally nobody wanted to be fancy either. So how do we convert from polar to our x and y? Well, we use the following formulas. R equals the square root of x squared plus y squared. Theta equals tangent or arctan of y over x. Feel free to take a screenshot of these. How do we convert back to our Cartesian coordinates? Well, we just do x equals r cosine theta, and y equals r sine of theta. So here are pretty much the equations you should memorize. All right. So fun fact is that our a plus b squared can actually be rewritten in polar form. And I'm not going to go through the derivation of that for multiple reasons, but I will be just explaining what's going on. As always, if you guys want a derivation, please just comment below. So basically, we will get this formula where our z, just an arbitrary number, I guess, is equal to r times cosine of theta plus I times sine of theta. All right. And another way that you can write this cosine theta, I sine theta, is by saying cis theta. This and this is the same thing. So essentially, we can rewrite this as r times cis of theta. And through this thing called Euler's formula and Euler's conjugate, we can end up rewriting all of this as r times e to the power of negative I times theta. All right. So why is Euler's formula important? Well, from Euler's formula, we get this thing called the Moivre's theorem, which I'll explain in a bit, but let's just go over with what we can do with Euler's formula, all right? Z in this case is simply a representation of our A plus BI, okay? So A plus BI is essentially equal to all of this, where I guess you can say A is like your X coordinate and B is like your Y coordinate. You can use that to convert between the two. So let me give a quick example of that before I move on. If we got A plus BI and we want it in polar, well, just have to do R is equal to the square root of A squared plus B squared. And theta equals tangent minus 1 of, I think it should be B over A. Yeah, B over A. Should be an A. Feel free to go ahead and take a screenshot. All right. So essentially, A plus BI can be rewritten as Euler's formula, where we have R times R, a constant, okay, E, the I, X, which is equal to cosine of X plus I sine of X. All right, the Euler formula conjugate, just R times E to the negative I theta. This is the conjugate, this is the Euler form. This conjugate here is just cosine X minus I sine X. All right. So let's say we want to have an exponent. Let's say we've got A plus B I to the power of n. That's just going to be like our z to the power of n, all right? So we do z to the power of n is equal to r times e to the power of, sorry, let me put this in parentheses, r times e to the power of I theta, also the power of n, which is essentially just going to be equal to r to the power of n times e to the power of n times I times theta. That's how you do an exponent with Euler's formula. Now, what if we want to multiply two things? Well, it's essentially the same idea, right? If we have A plus BI times A minus BI, or A plus whatever, they're both Z's, okay? Z1 times Z2, okay? That's going to just be R1 times R2 times E to the power of I, and this time we add our two thetas. Or X, I mean, whatever you want to call it. And then if we want to divide, same idea. We do Z1 over Z2 equals divide our R times E to the I, and this time we just subtract our thetas. It's multiplication and division. All right, so another just quick important relationship is the Euler formula relation to -1. And that's just that e to the power of I times negative pi is equal to -1. This is just a relationship you should keep in mind. If you want to go ahead and know why is this -1, well, just plug in theta equals negative pi, and then plug it into your r equals cis theta, which is just your, your cosine of theta plus Now this is negative, so this might end up being minus I sine theta, but try things out. It's either plus or minus I sine theta. And I think you should get out your R as being 1 or something like that. But anyways, fun stuff. So do we already go over expressing z in polar form? I don't think so, but I can just go over it quickly. So to express z in polar form, z equals a plus bi. Oh, right, yeah. R equals, again, square root of a squared plus b squared. And now for theta, theta equals tangent minus 1 of b over a. You might get multiple values. So it's always important that you make sure you check what quadrant b and a are in. It's like if they're in the first quadrant, it will be one thing, but if they're in the third quadrant, it will be something completely different. So check the quadrant it's in and adjust it for what value of theta you're going for. And as always, you can actually plug this into your r times ei theta equation right here. So final thing for this is the Moivre's theorem, which is actually kind of derives from the Euler's theorem. And it's that z to the power of n is equal to r to the power of n times, oh, I wrote this too big. Okay, so z to the power n equals r to the power of n times cosine of n times theta plus I sine of n times theta. All right, and this comes from the Euler thing where you had r to the n times e to the n times I times theta, right? Remember, because this part here is equal to this theta, essentially, which we can say is back again equal to here if we spread it out. So how do we find roots using the Moivre theorem? The roots with the Moivre theorem. Well, it's fairly simple. We've got our, let's say our z to the n equals a plus bi. And then what we want to do is we want to find the r cis theta version of z. So we want to convert this. So we have the r times cosine of theta plus I sine of theta. Now afterwards, we want to use this equation, which is theta plus 2 pi k over n. And n here is just our exponent. So essentially what we're doing is we're saying, okay, well, what angles of theta are we 0 at, or do we get our exponent at? So we can imagine a circle. If n is 3, we'll divide our circle in 3, okay? Or maybe if I should go like this, we'll divide our circle in 3, 1, 2, 3. If n is 4, we'll divide it in 4. And we'll end up getting these like spots on our unit circle as we go around. And then we can find the angles that will equal our roots. So let's say maybe our n equals 4, n equals 4. We'll have 0, pi over 2, negative pi, and 3 pi over 2. And essentially what we can do is we can take these angles and just input them in here, and we can get our zeros from that. I think it's easier if I have an example problem. Let me just go ahead and see if I can find one. All right, so I found a problem we can use. So let's say we have z to the power of 3 is equal to 2 plus 2i. So the first thing we want to do is rewrite it in our r times cosine theta plus I sine theta form. If you guys go ahead and rewrite it, we essentially get r to the power of 3, okay, times cosine 3 theta. Remember the Moivre's theorem, where we can convert our z to the n, plus I sine 3 theta. That's going to be equal to our 2 plus 2i. All right. So what we can do is we can find our r and theta using a and b. Remember, r equals our square root of 2 plus 2 all squared, and then theta is just our tangent minus 1 of 2 over 2. All right. So what we get is that our r cubed is going to be equal to, which one is this one again? Hold up, gonna check my calculator. Right, modulus. Right, so we get that r is going to be 2 root 2, and theta is going to be equal to pi over 4. All right. Or at least in this case, I guess r cubed is 2 root 2 because we're solving r cubed, which means that our r is 2. Sorry, root 2. Anyways, now what we do is we go ahead and we get 3 times theta, solve for theta equals pi over 4. Okay, so we can pretty much just divide the unit circle by 3. And what we will get is that theta equals -7 pi over 12, pi over 12, and 3 pi over 4. All right. So we are essentially going on our circle here, unit circle here. Okay, and we are making it so that our kind of domains are between 3 pi and negative 3 pi, okay? Between 3 pi, negative 3 pi. Instead of pi and negative, instead of pi and the negative pi. So we can go ahead and we will be considering 3 times theta equals pi over 4. That's between pi and negative pi. We'll also consider 3 theta is -2 plus pi over 4. So again, going around our circle. And finally, 3 theta is 2 pi plus pi over 4. And we can go ahead and solve these to get these values of theta. After that, all that we do is we just plug this in to our original equation up here, our cis theta equation, to get, so I'm just going to put our cis theta to get root 2 cis one of our angles, -7 pi over 112, and root 2 cis pi over 12, root 2 cis 3 pi over 4. So those will be our roots for z to the power of n. Hopefully that helped. If it didn't, please send me a question and I will be more than happy to answer it. All right. All right, so our next thing to go over is vectors. And aside from what vectors are and all that, there's really just, we're just gonna go over spherical coordinates, Cartesian to spherical, scalar product, cross product, using matrices, and I think that's about it. Maybe also the angle between two vectors, but those are just equations you guys can memorize and apply. Okay, so we remember from our 2D polar coordinates that we have a circle, right? I guess we have like this, where r is the distance from the center and theta is the angle that r makes with the x-axis. And of course, I hope you remember your x equals cosine theta, y equals r sine theta. Okay? Spherical coordinates are polar coordinates, but in 3D. Yeah, you also have cylindrical coordinates, but we're not going to go over that. Or at least I don't think so. So we've got our 3D here. We've got our x, our y, and our z. And essentially what we have is we have our r still coming out from the middle, but this time we've got two angles for this r. We've got our phi, which comes from the x-axis. And then we've got our theta, which comes from the z-axis, like this. All right? Spherical coordinates. Go ahead and take a photo. Now, to convert from Cartesian to spherical, or I guess in this case, yeah, Cartesian to spherical, our x-axis is our is equal to r cosine of theta, or I think this is spherical to Cartesian, my bad. Let me make some more space here. X equals r cosine times theta times sine of phi. Okay. Y is r sine of theta times sine of phi. And finally, z is r cosine of phi. All right. Feel free to take a screenshot. For Cartesian to spherical, our r value is just the square root of x squared plus y squared plus z squared. Our theta is the same thing as before, tangent minus 1 of y over x. And our phi is going to be cosine minus 1 of z over r. All right? So feel free to take a photo. Now we've got something called the scalar product. So the scalar product is essentially calculated using a b, right? Dot AB is equal to, I think this should be the magnitude of A times magnitude of B times the cosine of theta. And the cosine of theta is essentially the angle between vectors A and vectors B. All right. Cosine of theta is also equal to theta is equal to the dot product between A and B divided by their magnitudes. I'll show you guys how to find the dot product in just a moment. Okay, so vector dot product. All right, so let's say we've got vector A, which is equal to XA. XA. So let's just do X comma Y. And then vector B, which is equal to W comma Z. Find the angle between both of them. We are going to have to do cosine minus 1 of X times W. Okay, so regular multiplication, X times W plus Y times Z, okay, divided by the square root of X squared plus W squared times square root of y squared plus c squared. That's how you found the angle between two vectors. Use this formula here. Give you guys some time to go ahead and all right. So now what we're going to do is look at the cross product, right? So the cross product. I'm not sure if that past one was a dot product, but it definitely was the angle between two vectors. Yeah, it is 3:45 a.m. Okay. Cross product. Essentially, it is magnitude of A times magnitude of B times sine of theta. And you can use the previous equation to find that theta, or you can go ahead and use these with matrices. So I will show you guys how to do it with matrices. All right, so let's say we've got two matrices, okay? And they are going to be 3D matrices. Sorry, we've got two vectors. They're going to be 3D vectors. So A is going to be AI plus BJ plus CK. Vector B is going to be DI plus EJ plus FK. Literally, fuck. Yeah, me too. Okay, all right. So now we're gonna arrange this in a 2x3 matrix. We have I, J, and K. And we're going to go ahead and write out our A, B, C, D, E, F. And basically what we want to do is find the determinant of each of these matrices, like smaller matrices. And what we get is BF minus ECI minus AF minus DCJ plus, oh, ran out of space, plus AE minus DBK. This is the formula right here to find your cross product using matrices. I find this personally to be much easier than actually finding the angle, but of course the method is up to you. So that's where I'm going to stop here for cross product. If you'd like to see a video that teaches you how to do it step by step, just request it again in the Google form. I'll be happy to make a video. Actual problem. Okay. So the last part of this is derivatives. And let me just go ahead and check which derivatives the thing goes over. All right, so for this part of the video, I'm just going to assume that you guys know how to find derivatives normally. And I'm going to go ahead with the new stuff, or maybe it's new stuff for you guys, which is partial differentiation, all right? So partial differentiation is when we hold one variable constant, assume that it's a constant, and go ahead and just solve it as though it were one, all right? So let's say we've got x squared plus 2xy plus 3y squared. We want to find the partial derivative, let's say in, I don't know, response to x, maybe, okay? Partial derivative for x. I'm just going to write this as d over dx. That means we pretend y doesn't exist for just a bit, and we solve it with x. Derivative of x squared, 2x. Derivative of this one here, that's just going to be plus 2y, right? Y is a constant. It's not going to change. And this one right here is a constant. We assume it's a constant here. So it's going to equal 0 plus 0. All right. Now solving with response to y, same idea. X squared is a constant. Doesn't exist. It is 0. So that's going to be 0. Plus 2x here, a constant, 2x, and then plus 6y right here. All right. And those will be our two partial derivatives. All right, so now let's look at what they call higher order partial derivatives, which I think they just mean finding the second derivative. Let's say we have this function here, sine of x times cosine of y times x over y. And we're just going to find the second derivative with respect to x because I'm actually kind of tired. It's almost 4 a.m. It's kind of tired. Let's go with f with respect to x. Let's find the first derivative. Well, first derivative of sine is cosine of x times cosine of y because y is a constant. So this here is pretty much treated as a normal number times 1 over y. Why 1 over y? Because here we've essentially got x times 1 over y, which is equal to x over y. We know y is a constant, so 1 over y will also be a constant and will not change. All right, so that's our first derivative. Finding the second derivative, same idea. We just pay attention to the x. Here, cosine of x, second derivative of that, ends up being negative sine of x, cosine of y, a constant, so it's going to stay as cosine of y. And finally, in this case, well, 1 over y was always a constant. So I guess in this case, it just becomes 1. All right. And let me just check my, oh, it's plus, it said plus. Sorry, this is plus. That's why it becomes 1, my bad. That's why it's 0, sorry. Otherwise, this here would be 1 over y, my bad. But because it's plus, that goes to 1 over y for the first derivative, and then it goes to 0 for the second. And you end up getting this for your second derivative. Okay, so the next thing that says here is finding stationary points. And let me see. Okay. All right. So we'll do vector differentiation after this. Let's go with stationary points. You know what? I'm just gonna. Yeah, we just call them maxes, mins, and zeros. I don't know what the fuck a saddle point is, but stationary points. Fuck, who calls it that? Okay. No offense to anyone who does call it that, but just make your life easier. You may pretend to be a fancy Oxford student. You don't even go to Oxford. I mean, anyways, real quick, real fast. Maximum. It is when you have something like this. Okay? When it is like this means that the derivative, okay, the second derivative is less than 0. It is 0. Okay? So f, second derivative of whatever variable you want, is less than 0. In this case, they're also saying here that second derivative of f times second derivative of y is greater than the derivative of f and y squared. Okay, very cool. You can just use the first derivative to see if it's 0. F double derivative of f first derivative of a equals 0. And you can check that for both of your values. Well, yeah, because you want to change both of them to be 0, okay? Minimum, same idea. F double derivative of A is going to be greater than 0, it is positive. And F first derivative of A, you also want that to be 0, okay? Because think about it like this. This here's your minimum. Just right here is 0. Where it's at the minimum, the first derivative equals 0. That's what you want, okay? That's it. I don't know what the fuck a saddle point is. Inflection point, that's just where your second derivative of whatever is equal to 0. Okay? The first derivative, however, can equal an arbitrary number. Go ahead, take a photo, take a screenshot. If you have any questions, as always, fill out the Google form, and I'm more than happy to go ahead and look through them. Okay. Okay, so finally, differentials for vectors or a vector valued function. I'm going to make this one really, really simple, okay? So we know that vectors, if you didn't know this already, they can be written with I hats and J hats. So basically, let's say we have a vector A, I don't know, and it's going to be with B comma C. This can be rewritten as B I hat plus C J hat. And if you add a third value, it's going to be K. If you remember from when we were doing matrices earlier, we had those I, J's, and K's, that's where they come from. Because vectors can be expressed in this format. All right. So let's go ahead and do some derivatives with this. So let's say we have this vector R of t, okay? It's with variables in respect to t, and it's going to be equal to x of t I hat plus y of t j hat. Essentially, this is just describing the vector r, which is equal to x comma y. And x comma y can both be rewritten with t's, okay? So now what we're going to do is we're going to differentiate this. So we're going to get dr over dt, right? Because we're differentiating with respect to t for everything. Is just going to be equal to dx over dt I plus dy over dt j hat. Okay? So essentially what you can do is you can multiply both sides by dt. And I'm just doing a derivation here. It's okay if this doesn't make sense to you, but go ahead and you cross out these dt's. And we get that the derivative with respect to r is equal to the derivative of x of t, right? dt, well, they crossed out. Anyways, you get dx times I hat plus dy j hat. And this is essentially the formula you need to follow. And let me find an example real quick that I can just run through quickly. All right, so let's go ahead and say that we have this vector r that's defined by x comma y. And in this vector, x is equal to t and y is equal to t squared. So what we're going to go ahead and do is we're going to go ahead and write this in our I hat j hat form, where r of t is going to be equal to our x I hat plus, oh, I ran out of space, y j hat, okay? This is what we define x and y as, so we can rewrite this as r of t. Sorry, let me take out this t. Now we're rewriting it as r of t equals x is just t, so t I hat plus t squared j hat. And as we saw earlier, we can just take the derivatives of each of them. All right, so we're going to go ahead and just differentiate this. R naught of t is going to be equal to 1 times I hat plus 2 e times j hat. Sure, you can just go ahead and rewrite this as a vector as 1 comma 2t. And that's my very quick example on vector differentiation. Of course, if you have questions, you want some more examples, you want me to run through a problem, link to the website should be below. It's also on the YouTube About page. Feel free to check it out. Go ahead and subscribe and turn on notifications. It is now 4:08 a.m. I am exhausted. If my videos have any inconsistencies, please tell me. I am more than happy to remake them. I'm a very tired college student. And yeah, I'm gonna go faint. You kids do whatever you guys are gonna do. Hopefully this video is helpful to you guys. And yeah, all right. Awkward goodbyes. And where's the mouse? Okay.